So, Tom, it's an absolute pleasure to talk to you. I'm a huge fan of NASA, and I'm astonished by everything that you do. Can you tell us, firstly, what your position is there and what your mission is, if I can use that terminology?
Sure. Well, thanks, Phil. I work at NASA headquarters in Washington, D.C., where I work in the Planetary Science Division and the Planetary Defense Coordination Office, which is one of the best named offices to work in. And we are really excited because our DART mission, the Double Asteroid Redirection Test, is coming to a culmination on Monday evening U.S. time. That'll be Tuesday morning Australian time.
Right.
We are deliberately crashing a spacecraft into an asteroid when we don't need to. This is not a dangerous asteroid. So we're doing this test when we don't need to do it on an asteroid that isn't dangerous in order to learn how to do it if we ever discover an asteroid that really is dangerous.
Of course.
And we have to.
Well, let me stop you there, Tom. Everything that NASA does is important. So there is definitely a necessity to this. In fact, obviously you may have seen, they did a documentary a few years ago with Bruce Willis, where he had a simulation of him landing on an asteroid, trying to blow it up. And, I mean, that's, to me, says don't trust the private sector, because they always overcomplicate things. Leave it to the experts.
Well, I don't want to get into trouble there. I mean, the private sector did launch our spacecraft. SpaceX gave the DART spacecraft a terrific ride on their Falcon 9, and we're headed in exactly the right direction.
Yeah, but you wouldn't let Bruce Willis on board. That's my point.
Well, that's fine. But I mean, when you're, okay, there are some things that you want an actor to do, but for, flying your airplanes and operating on your knee and deflecting your asteroids, I think you want the professionals to do it.
Of course. And with that in mind, can I call it a spaceship? Would that be fair to say? Is that what it is?
It's fair. We call it a spacecraft.
Spacecraft, right, okay.
Because it's pretty small. It's about the size of a big vending machine with big solar panel wings on it. So it's
right, it doesn't have a pilot then, of course, unless you've got a mouse as a pilot.
No, we would not send a crewed spacecraft to crash onto an asteroid. That would be cruel.
Of course. But this is, pardon me if I'm incorrect about this, 20 million miles away?
It's about 11 million kilometers, so that's about 8 million miles.
8 million miles, okay.
From Earth at point of impact. Right. And that was by design. I mean, Earth is a planet. Earth is in orbit around the sun. Asteroids are also in orbit around the sun. And the only asteroids that are ever a danger to the Earth, or ever a hazard to the Earth, are the asteroids whose orbits intersect with the orbit of the Earth.
Right.
And even then, nothing bad happens unless Earth and the asteroid arrive at that intersection point at the same time. Okay. Now, this asteroid we're doing a test on doesn't intersect the orbit of the Earth, but it does come close. And so we're timing this test to happen when this asteroid is relatively close to Earth in order to get really good bandwidth, really good data back.
Right. And how did you select the asteroid?
Well, I can't claim credit for that. Other members of the team selected the asteroid some years ago. And the virtue of this asteroid is that it is a binary asteroid. It's a double asteroid. That's part of the double in the name of the mission. It's a small asteroid about 160 meters across that's orbiting around a bigger asteroid about 800 or so meters across. And it goes around once every 11 hours and 55 minutes. Right. And we know this because our view from Earth is in that plane where we're going around. And so we don't literally see the two asteroids, but we see the total brightness of the two of them shining in the reflected sunlight. Right. And every time one goes in front or behind the other, we see a little bit of dip. A dip in the brightness. Yeah. And those things happen repeatedly, every time around. That's how we know the orbit is 11 hours and 55 minutes. And so after we execute this impact on the smaller asteroid, we're going to change that orbit by just a little bit. So it'll be like if you drop your wristwatch, for those people who still wear wristwatches, if you drop your wristwatch and it starts running a little bit fast, you might not notice the next day, but a couple of weeks later, you will notice that things are not happening at the right time anymore.
Fantastic.
So absolutely. It was a really brilliant idea. I credit that to Dr. Andy Cheng at the Applied Physics Lab.
And how did you get the spacecraft to where it's going? How long did it take?
Well, the tricky business, of course, is, like I said, Earth and the asteroid are on an orbit around the sun. And so anything we do in interplanetary space means we have to get our spacecraft also into an orbit around the sun that gets to where our destination is at the right time.
Right, of course.
And so we launched DART last November 23rd. And so it's been since then in cruise on an orbit that's sort of close to the orbit of the Earth, but not quite, on track to meet the asteroid Didymos, specifically the asteroid Dimorphos, that's the little moon one, next Monday.
Wow. The maths on that is unbelievable. We can't get the trains to run on time here. We still have timetables, and they're only coming from up the road. NASA can get things done on time. That's what I like about NASA is when they say the space shuttle will be arriving back on Earth at 9, 11, and 15 seconds. Bang! There it is. Always on time. I like to call that NASA time.
And the reason is you can't stop gravity.
Yeah, well, there's that too. In fact, and with that in mind, I'd like to, with your help, because I understand how it works, but also because we have some visuals here, I'd like to show the people, and perhaps with your help, how I understand how the procedure is going to work, if that's okay.
Sure.
Using obviously crude devices such as a cat toy, which obviously takes the part of the asteroid, right? I mean, is it close? Obviously, the asteroid will be a more sort of metallic gray than this cat ball.
We know it's not that color, definitely.
Right. Okay.
But it's probably pretty gray. Actually, we really know very little about this asteroid specifically because it's so small. We know it exists. We know roughly what size it is, but we don't know what shape it is, and that's one of the things that makes this very, very difficult. Right. Because the engineers have had to program the computer on the spacecraft to interpret the images that our telescopic imager is feeding it once per second in the last 4 hours, recognize which dot in that image is the thing we want to target, and steer the spacecraft to it so that it hits it at a speed of 14,000 miles an hour. So there's no opportunity to turn around or to wait.
Right.
And we have to teach the computer to recognize an object that we don't know what it looks like. We're just approximating.
Yeah, of course.
And so it's a very difficult thing to do.
Well, it doesn't look exactly like this for the people that are looking at it, but for the sake of imagination, and for the spacecraft, I found obviously the cat toys have been brilliant. This giant mouse, if you press its nose, it has a sort of space-like look and a tail, which I'm presuming we're going to use in this instance for propulsion. So here comes the DART. There's the asteroid. 14,000. In fact, we should get some space too. Can we cue the space so I can actually have the whole atmosphere? Got some space in the background there. So here comes the asteroid. Here comes the DART. Gently pushing into it, or
no? Because okay. So your scales are a little bit off. So if you wanted to do this at full scale, your asteroid would be kind of a small football stadium full of rocks.
Right.
And your spacecraft would be a vending machine or maybe a golf cart.
Yeah.
Okay, so that's about the right.
We're going to have to suspend disbelief on this one then, Tom.
Right. So the cat toy isn't going to work, but the visual is you're running your golf cart vending machine into the side of your football stadium full of rocks at 15,000 miles an hour.
Yeah.
So that's not a gentle push. There is a push because it arrives with some momentum, but there's also a lot of energy released. And at that speed, the spacecraft is carrying a kinetic energy of motion that is far, far more than the same mass of high explosive.
Right.
So you're releasing a lot of energy. You're digging a big hole in the asteroid and taking a lot of that material and blasting it out into space back in the other direction.
Right.
Which acts like a little momentary rocket engine and gives the asteroid another push in the same direction. And that's the real beauty behind this technique.
Of course.
It's not just a gentle push. It's a push plus a big bang.
Of course,
an extra push.
Did you toy with the idea of a nudge?
Not really, because, there's a nudge and then there's a nudge, right?
Yeah.
Because really the essence of planetary defense is you're not trying to destroy the asteroid. You're just trying to give it a nudge, which is to say, change its motion by a little bit way in advance. So that event that you're trying to prevent, which is Earth and the asteroid arriving at this magic intersection point at the same time, just make the asteroid 10 minutes early or 10 minutes late, then you don't have an impact,
Yeah,
and
of
you have a
course.
good day instead of a bad one. So the idea of planetary defense is to discover these asteroids, all the ones that are potentially dangerous, very early. So we have years of lead time, and we can give the asteroid a small push. Maybe it needs a spacecraft moving at 15,000 miles an hour to do it,
Yeah.
but make a small change in the asteroid's motion so that it's late or early to the party and does not
It's a
arrive.
terrific idea. Brilliant concept. Seems simple to the layman, but for those of us that know, it's a whole other kettle of fish.
Well, but that's the beauty of the whole thing, right?
Yeah.
It should be conceptually simple. So the principle is easy to understand, even if actually making it work takes 21st century technology.
And people can watch this, Tom. People can actually, but you've got a camera there.
Absolutely. So NASA TV and also NASA.gov, NASA Live, also on social media, will be streaming everything live Tuesday morning your time.
Right.
So the impact is, I'll say the broadcast starts at 6 p.m. East Coast US time, which I think is 8 a.m. Tuesday your time. And we will be streaming back images from the spacecraft at 1 per second. The whole world is going to see everything that we see, everything the controllers see in real time. And what we expect to have happen is a lot happens very fast at the end, only in the last hour, because remember, it is 14,000 miles an hour. And so we're very, very far away from this fairly small asteroid until the last few minutes.
Yeah.
Only in the last maybe 45 minutes or so do we even see the small asteroid that we're aiming for.
Wow.
And we don't see what it looks like. It's just a dot until maybe the last half hour. So we are going to be, well, I'll admit my palms are going to be sweaty. I don't know what the others are going to be feeling, but it's going to be tremendously exciting seeing these images come in 1 per second and the asteroid getting bigger and bigger and bigger and bigger and bigger, eventually filling the frame and stop.
Wow. You don't want to get the wrong asteroid and cause some space rage. That's a lot.
That's right. No, but we want to see the asteroid filling the field and then confirm loss of signal from the spacecraft. And at that moment, that's when the first test we're doing ends and the second test starts. Because the first test is, can we actually do the kinetic impact? Right. The second test is, how does the asteroid respond? Because it's one thing to destroy a spacecraft, but the question at the end of the day is, did we move the asteroid?
Yeah.
And by how much did we move the asteroid? Did we accomplish what we were trying to accomplish?
And how long will that take for you to have that information? Will that be immediate?
Right. Right. So that's what I was talking about before, that it's like you've changed the ticking of your clock and you have to wait to be able to see that. So we will have astronomers on the ground, and we'll also be using telescopes in space to see what happens in the short term. We should see a brightening of the object, as there's a lot of dust that gets kicked up and it gets lit up by the sun. So we should see a general brightening. And then maybe a week or 2 or 3 after that, we'll detect the difference in that orbit. And as time goes on, the longer we wait, the more precise a measurement we get of that change.
Fantastic.
And the more precisely we know exactly what happened.
And as I said before, when it comes to precise timing, you can't get more precise than NASA. Have they named anything after you yet? Because I can tell it was a bit of an issue when I said they called it Tom. Have they got anything? Can they give you one?
So, well, there's a lot of intricacies there. So near-Earth asteroids cannot be named after living people or even dead people, because you never want to have the circumstance where something named after Phil, for example, comes to destroy the Earth.
Yeah, that's right. Yeah, that would be bad for me and bad on Instagram. I totally get that.
But it is true that asteroids out in the main asteroid belt, out beyond the orbit of Mars, that never come close to the Earth, the prerogative to name those asteroids goes to the discoverer. The discoverer can nominate a name, and if it passes the rules of the International Astronomical Union, it can be adopted. And there are a lot of asteroids, and there are a lot of scientists working on asteroids. And so currently, as things are, if you have made a significant contribution to asteroid science, one of the discoverers will decide to name an asteroid after you. And so I have the privilege of having an asteroid named after me, which is not quite as cool as it sounds, because even though, like I said, it's the discoverers. So even though there are asteroids named after Beethoven and Einstein, there's also an asteroid named after Phil Spector. And there's an asteroid named after Mr. Spock, not the TV character, but the cat owned by the guy who discovered the asteroid, who was a Star Trek fan.
They've watered the whole thing down, really.
So it's a very, very strange and eclectic club. The people who have asteroids.
Well, I, as far as I'm concerned, yours is the most important moon in the sky, Tom.
Yeah, but that's not. But this is, the asteroid named after me is somewhere else. So we're the DART mission is the asteroid Didymos and its moon Dimorphos, and that's what it's going to stay.
Well, when I look up tonight at the sky, I'm going to be looking for you.
Okay, fine.
Well, both of you, both your job and the more important part, the real Tom.
All right, I appreciate the thought.
It's such a pleasure to talk to you. Thank you so much. Good luck Monday night.
Oh, thanks so much, and good luck to you, and hope everyone's watching.
Thank you very much.